We wanted a new driving experience, so we built one.
It's a fully head-tracked first-person view setup. But what makes our rigs significantly different than all the rest
is the lean out.
The entire camera system pans, tilts, and physically leans out the window on a third servo.
It sounds insane, but it works.
And it feels like driving a real truck on real trails.
Lean out the window? Oh, hello.
Oh, hello. Over the last year, we've been refining the whole entire system to make it stronger, smoother, and way more reliable. So in this video, I'm breaking down the whole project clearly.
What the platform is, how it works, what powers it, what we fixed, and what we upgraded for this version. Let's get into it.
Oh my God!
20 pounds.
We started with a stock SCX6. The first major change was the body. We removed the Lexan from the factory mounts and hard mounted it directly onto the chassis. That way, when the body opens like a clamshell, the entire interior stays attached to the truck and we get full access to the FPV system without the body lifting the electronics with it. Inside the cabin is the full FPV assembly. The pan, tilt, and lean servos are mounted in the dash area.
Everything FPV related is on this tray right here.
The head tracking hardware is there. The secondary receiver is in there. The FPV components stay on the chassis so we can get to them quickly whenever we need to work on the system.
The only thing that comes from the chassis itself is one power wire that comes directly from our two 3S batteries that are being run in parallel.
Everything FPV related runs off of one custom power breakout box. The truck's 3S battery comes in at about 12 volts, and that goes into the breakout box with a switch.
I built this little tiny breakout box that splits the 12 volts coming from the chassis battery into three 12-volt outputs.
From the breakout box, one line goes straight to the video transmitter and camera, another line goes to the BEC that powers the second receiver and all the servos for the pan, tilt, and lean, along with anything else in the cabin that runs off of standard 5-volt receiver power. That includes a cooling fan for the video transmitter because those transmitters run hot and need active cooling.
It's all wired through a switch, so we can actually turn off the whole FPV side of the truck with one switch.
For control, we're using the Radiomaster ELRS MT12.
Welcome to HTX.
We chose this radio because it can run a large amount of channels across many receivers all at once.
And it has a trainer port. The trainer port uses a simple 3.5mm input and lets us feed head tracking data directly from the head tracker into the radio.
A feature found only on flight radios until now.
The MT12 sends all of the normal driving commands to one receiver in the truck. That receiver handles steering, throttle, the lights on relays, and the 2-speed shifting servo. The second receiver handles the camera system. That's where channels 6, 7, 8, 9, and 10 go, where we're using 7, 8 for pan and tilt, and channel 9 for the lean servo.
I bet you're wondering how we connected to two receivers with one radio. Well, this MT12 Radiomaster is running the ELRS protocol.
ELRS, or Express LRS, is an open source radio control system that was originally developed by FPV drone pilots who needed as little delay, as long range, and as rock solid signal as possible. Because it's open source, it evolves super fast, gets constant updates from the community, and delivers performance that rivals all proprietary RC systems, which is why it's now spreading well beyond drones and into all kinds of RC projects.
We are using two ELRS receivers. ELRS lets us connect to as many receivers as we want. The caveat is that only one of those receivers can have telemetry enabled. And if you leave them on for over a minute without connecting to a radio, they will go into Wi-Fi mode. That's right, they have Wi-Fi. You can connect to them through your phone, and in there's a plethora of settings, and that's where you can turn off telemetry for your receiver, and there you can change your channel mapping.
On my truck, I'm running the Caddy X Avatar HD system. Nash is running the DJI Air 03 unit, two completely different ecosystems, both powered off the same 12 volts.
That's pretty much the whole system. It's not superly overly complicated. All the magic really happens in the MT12 radio and also the head tracker.
Our head tracker is an open source project running on a Chow Seed microcontroller. We flashed the software from GitHub, and it's been the best head tracker we've used so far. We've tried other systems that use magnetic north, and those drifted consistently.
Did it stop drifting shitty, or is it still drifting stupid?
I'm drifting shit.
Is it drifting?
Maybe it'll get better as we go.
This one barely drifts at all.
It's so good with the head tracking.
The head tracker connects to the MT12 through a 3.5 millimeter jack. That cable sends all the head tracking data straight into the radio.
Oh, there's a fly on my camera.
Come on. Want me to knock it off?
I shook my head.
Oh.
A double tap anywhere on the goggles sends a receiver command, which is important because the servos do not know anything about the head tracker itself. If a servo ever creeps off center, we can recenter the entire system instantly.
I had my neck all wrenched around because I lost my center.
Double tap it. Hold on, I gotta get up on this rock.
The head tracker needs its own 5-volt power source. On my goggles, I'm using a small BEC that runs off of the main power and steps it down to 5 volts for the microcontroller. Nash is using a short USB-C cable because his goggles provide a 5-volt USB-C output, so his microcontroller can be powered directly from that port. Right now, the head tracker must be tethered to the goggles for power, and it must also be tethered to the radio for head tracking. If Radio Master eventually releases an MT12 with Bluetooth support, this head tracker could run completely wirelessly, which would remove the cable to the radio entirely. For now, both the power cable and the head tracking cable are required.
Oh, I'm pretty deep now. Maybe I should lean in.
I'm pretty stuck. What's going on here?
For the pan and tilt setup, we're using Reefs micro servos that rotate a full 180 degrees.
Yes. No. Out the window I go.
That extra travel is what lets us look where we actually need to look. We can check the front wheel, we can check the rear wheel, we can look up, we can lean out the window, and just get a much wider view from the driver's side. Most radios only give you around 90 degrees. So we tried one of those Amazon servo extenders to stretch the signal. It worked, but it was super jittery. The servos twitched nonstop, and it made the whole thing feel rough. So we built our own. We used a small Arduino Nano to widen the signal properly and add smoothing in the code so any little jitters from the head tracker get filtered out.
All right, we're here, we're FPV'd, and we have a new servo extender, which is quite a bit smoother than the last one. Oh wow, is it ever? Oh dude, this is great. This is really great.
We're not programmers, but ChatGPT wrote the extender code for us. We just loaded it onto the Arduino, wired it, and it worked. And honestly, it's the smoothest thing we've seen available anywhere.
Yeah, I asked ChatGPT to write me a code that extended our radio signal pulse width because the radios can't provide enough to get the servo to go 180 degrees. And hey, I'll show you the code right here. You guys want to see the code? You can see it right now. Yo, ChatGPT, can you hear me?
Loud and clear. I've got you.
All right, listen, I've got a 180 degree servo that can turn 180 degrees, but my radio can only spit out a PWM signal to get it to turn 90 degrees. Is there any way to program an Arduino to do a better job scaling the PWM output from my Radio Master MT12 to get it to turn the full 180 degrees?
Absolutely. You can use an Arduino to read the PWM signal from your radio, map that incoming pulse width range to a full 180 degree output, and then output a new scale PWM signal for the servo. Basically, you read the input pulse, do the math to scale it up to the full range, and write that new pulse out. It's a classic remapping job.
Great, but then can you also add some kind of smoothing
You can implement a smoothing function by averaging the last few readings. For example, you could maintain a small buffer of recent values and output their average. This smooths out sudden jumps, but still keeps it responsive. You could also use something like an exponential moving average to give more weight to recent input. That way it stays steady, but still reacts naturally.
Write me the code, enter. Boom, okay, so here's a clean, proven Arduino code that does exactly what you want. It reads PWM, scales 90-degree radio travel to full 180 degrees, adds smoothing that kills jitter without adding noticeable lag. Way better than those cheap Amazon servos. Great, okay, cool. Oh, see, sweet. So I literally just paste this code out of ChatGPT. What's cool about ChatGPT is that in the Arduino code, it just says what each part of the code is responsible for. So here you can see there's a smoothing factor, there's a read receiver pulse section, there's a clamp receiver input, there's a map RX range to full servo range, there it is, exponential smoothing that kills jitter and keeps response fast. Anyway, there you go, check it out. We just wrote Arduino code that works just by talking, like literally talking to the computer. Oh, we're all doomed, aren't we? We're all freaking doomed.
Oh, it's so good. These work so well. Okay, yeah, just go slow now.
Yeah, have I got the angle straight?
I feel like you got the angle. Yeah, let me.
Once we switched to the Arduino extender, the head tracking finally felt right and tight. You turn your head, the camera follows, and there's no twitching or hesitation. It just feels super natural.
Yeah, you good, Nash? You recording or you hit me? Hey, what are you doing over there?
We installed the Reefs Beast 1000 steering servo into the truck. It's one of the strongest servos on the market.
Oh yeah, boy.
And even at 6 volts, it's completely overpowered for the SCX6. We're planning to bump it up to 8.4 volts.
Wow, it can pull a lot of amps, eh?
But before we do that, we need to stiffen the entire front end because the SCX6 comes from the factory as a complete wet noodle.
You can see how flexy they are, eh?
The front of the truck is a 3-link with a panhard, but the panhard mount on the chassis is plastic.
That whole panhard mount.
Yeah, you can see it moving here.
The hub mounts are plastic. The steering linkages are plastic. Pretty much everything that matters is plastic. So when the truck is under load, the whole front end flexes instead of letting the servo actually turn the wheels. That's why Nash will sometimes think the truck is steering itself. It's not the servo, it's the whole front end bending.
Stop turning your wheels to the right. It's just doing.
So we upgraded with the best hop-up parts available for the SCX6 made by a company called Vitavon Racing.
There's no better parts than Vitavon parts. You should get yourself some Vitavon parts.
Very good.
They fit so well. What a pleasure.
We swapped in aluminum C-hubs, aluminum steering knuckles, a full aluminum steering linkage, an aluminum panhard mount, and an aluminum panhard bar. We also added an aluminum servo mount to eliminate the slop you get from the stock setup.
Look at this.
Vitavon also makes pretty much every upgrade part you can imagine
so
for the SCX6 and a ton of other RC platforms.
Come on, Vitavon, that looks so insane.
They make some of the best CNC parts in the hobby, so if you want to completely transform the feel of your rigs, definitely check out what they offer. On top of all the steering upgrades, we also picked up a set of their aggressive tires, which we're going to compare to the stock ones in our upcoming romping videos. And yeah, we grabbed some of the nicer details too, like their diff covers and their hardened steel axles. They don't affect the steering directly, but they're tough, they look sick, and they add some good weight where you actually want it.
Like coming around you.
Whoa.
Okay, recording. Just started recording the Osmo.
We never planned for this project to become what it is now.
Oh, I'm 240 feet in the air right now, so I'm coming down on you while you're leaving the parking lot. That's cool. It's like little 1/8-inch scale little guys.
It started as a small experiment, and somewhere along the way, it turned into one of the most rewarding RC builds we've ever worked on.
Oh no, upside down in the water, oh no.
What?
Flip me over.
Oh, shit.
Every improvement led to another idea, another redesign, another test. That constant evolution is the part that keeps us hooked.
What's better than an SCX6?
2 SCX6s. Oh my God.
20 pounds.
People have said we're gatekeeping, but that's not what's going on. The only thing I'm protecting is the process. We didn't buy a kit that bolts parts together. We went through real iterative design. We molded pieces. We printed them. We discovered what didn't work.
I had trouble calibrating in my apartment.
We changed it. We reprinted it. And we repeated that cycle until everything finally behaved the way we wanted it to.
Out the window we go.
It took actual time, actual mistakes, and actual problem solving. That's what gives the project its value.
Whoa, turn on the lights.
So I'm giving you the most important information here. I'm showing you how it works and the major decisions behind it.
Okay, now you're on my camera.
Oh.
You gotta go back. Oh, shit.
What I'm not doing is handing out every exact measurement of the STL or geometry file. That last stretch is where you learn the same way we did. And honestly, you might come up with something cleaner or smarter than we ever could build. That's the part I want to see. I'd rather watch people push this idea forward than just copy our final
The
version.
wheel hit me right in the window. Perfect.
Broke it. Hand hard mount. Broken.
If you want a setup like this, build it. Be your own tech support. Figure out the lean out geometry. Figure out the wiring. Figure out the tolerances. That's the whole point of RC. The process is what makes it satisfying.
Yes! Kevin's like, yeah!
That's the guy that caused
So
it.
here's the challenge. Build your own. Show us your lean out rig. You've got more than enough information to start, and the rest is the part we've earned through trial, error, and stupid amounts of hours. That final step is yours. And what you learn from this experience is exactly what makes it worth doing. K-pop out.
Oh, the fly's back. Oh my God, he's still there.
Uh-oh.